Our next speaker, Professor Pulleyblank, is the Vice President of the Center for Business Optimization for IBM Business Consulting Services. He's author or co-author a number of scientific papers and books, for example, Combinatorial Optimization by Cook, Cunningham, Pulleyblank, and Schneider, published by John Billy and Sons in 1998. Pulleyblank's research interest is applications of optimization as well. He has consulted for several important companies, including Mobile Oil, helicopter routing, Marks & Spencer, and depot management, Statistics Canada, and survey validation, CP Rail, and plane scheduling. The title of his lecture now, Alternative Pace, and US patient number 5905666.
It's doing something. It stopped doing anything. Good. I think it's coming to life. First of all, thank the organizers very much for inviting me here, and what a pleasure it is to be here at this meeting. When Professor Kuhn was speaking and talking about the Hungarian method, I was thinking back to when I was a doctoral student at Waterloo in Jack's class, and the excitement of when he first showed us this method. And it was one of these moments in your mathematical career when you think that there really is order in the universe, because everything just falls into place, and it worked. And it really is a pleasure to be here. What I want to do today, however, is talk about something else, which is related. Alternating paths and US patent number, whatever it is. And this is joint work with Alan Hoffman, John Tallman, and myself, which we did at IBM. And I thought it would be interesting to talk about for several reasons. First of all, this may be the first talk at a combinatorial optimization meeting on a patent. I'm not sure. Secondly, Alan Hoffman and I were speaking just last week, and he did ask me to repeat his regrets that he was not able to be here for this meeting, so he asked me to send that on to you. There's a third thing which I should just point out. Do you notice the background picture? For those of you who don't know what I've been doing lately, I spent the last 5 years building the world's most powerful supercomputer. And the nice thing about supercomputing is, anybody can say they have the best algorithm, but there's some debate about what the metric is. Supercomputing, they make it easy, and there's a list that's published. And the list says, what's number 1, what's number 2. And that's a photograph of number 1. This photograph was taken last week at the official inauguration of this Blue Gene supercomputer at the Livermore Labs in California. Just to give you an idea, that's 130,000 processors capable of performing approximately 250 trillion floating point operations per second, which you can solve pretty big assignment problems on. Now, what I'm going to talk about today is an application that comes out of computing, but in particular how it comes back to a theorem of printing, and it relates back to much of what we've been talking about. First of all, there's the patent. This is real. photographed it, I scanned it in from the official patent document. Any questions? It was an interesting problem because where the problem came from, in fact, was from a problem really from linear programming. And it came from something which is so simple that it would hardly be even dignified by being called an algorithm. And that is simply this: how do you do left and right multiplication of a matrix by vector? So how do you compute AX, or how do you compute YA? Vector times a matrix, matrix times a vector. Of course, these are quite fundamental operations, correct? If you look at linear programming, we do a lot of that. If you think of the simplex algorithm, of course it tells you there, which do you do more? The left multiplication or the right multiplication? Well, you can say, are you thinking primal or dual? But if you think of the primal simplex algorithm, you do enormous numbers of this YA computation, right? Because if you think of the simplex algorithm, what it's doing is this pricing operation, where it prices out the columns to decide who's going to enter the basis. And every time it does pricing, it effectively does that operation. On the other hand, it does the AX calculation basically when it checks feasibility. So it is much rarer operation. So this computation is critical. When we came to interior algorithms, there was an interesting change in the world because all of a sudden it was not just so critical to only do the one side. In fact, the interior algorithms do about the same number of both calculations. And that made the world all of a sudden get a little more complex. And part of the reason for it is this, and it comes back to computers. Computers are very concrete objects. And as soon as you start looking at an algorithm that you're really going to implement on a computer, there are issues that come to the front, like do you store the matrix by rows or by columns? And depending on which calculation you want to do, one is much better than the other. So in particular, if I know I'm always going to be doing one type of calculation, I can use data structures which support that, and life is easy. But if you have to use two sometimes, it becomes more difficult. And here's the other thing that makes it difficult. Life is sparse. If we look at a typical problem, let's suppose for a minute we're doing this calculation, which is basic to the simplex algorithm, this YA greater than or equal, or Y, just computing YA. There's our matrix A, there's a vector Y, and so I really have to take this vector times the elements in some column and do the inner product. If you look at the types of very large linear programs which arise in practice, they're not just sparse, they're really sparse. And by that I mean, you may see, typically, it says here, typically 4 to 8 non-zeros per column. Now, I didn't say how big the matrix is, but I'll show you examples in a few minutes. You could have matrices with tens of thousands of columns, thousands of rows, and they still, in practice, will have this kind of property. They're very, very sparse. Now, you see, why that matters is, as you can imagine, is if I've got a column such as this, which has only got a very small number of non-zero entries, and I'm worried about efficient computation, I don't really want to be doing all those products with the zeros as I work it out. I want to find a better way of storing it, a better way of doing the computation. And in fact, one of the methods that is used in some cases is to take the matrix. You can reorder the columns, that makes no difference. And you reorder them based on the number of non-zeros. So you'll end up with a small submatrix, which has got a lot of non-zeros. And then you end up with other submatrices, which have smaller and smaller number of non-zeros per column. Make sense? And in fact, then I can also store it in a much more compact fashion, because in fact, all I do is store, first of all, the indices in each column of where the non-zeros occur, and then I put the values themselves. And by doing it this way, I get one of the sparse matrix representations. Now, suppose I've done that. As soon as I've done that, I can start doing my computation, and now I can focus on just one of these little dense submatrices. You see what I did there? I said, let me just now take, for example, one of these submatrices, which is now completely dense,
All entries are non-zero. These are the indices, these are the values. If I worry about it, then I say, well, now here's what happens is I've got my y, I've got the non-zeros, and I know where the non-zeros are here, I know where they occur, and now I want to compute the inner product. Make sense? Straightforward, you'll see how to do it. And now here's where life gets more difficult again. One of the techniques that was introduced in computing to try and speed up computation for matrix vector type of operations was array processors, vector units. The idea of these was to say, instead of just doing scalar operations and then adding it up, why don't you do it in parallel? So you can take a large number of entries, multiply them together, and do it all effectively in one operation. So for example, if we did a normal scalar computation to compute this inner product YA, we would find, for example, on one machine we looked at, it was approximately 18 machine cycles for a calculation, and it took 15 cycles to initialize it, if we did the scalar computation. On a vector unit, however, you pay a larger price to get it started up and running, but once it begins to run, then it does a single calculation in only 4 cycles. So you see it becomes much faster with your vector unit, provided you can overcome the startup. And if you take that criterion, it says it's around 12 elements at which it breaks even. So if you have more than 12 elements in the column, your vector unit is going to start helping you. If it's less than that, it's probably not worth using. Are vector units useful? Well, if you put together the two things I said, number one, the break-even point is 12. And number two, the problems are very sparse and typically have 4 to 8 non-zeros in a column. You would immediately think, well, perhaps vector units are not so interesting. But there was a very elegant solution to this, which was actually discovered by John Forrest and John Tomlin. And they said, you know, when you do this calculation, y times the matrix, what you can do is, in fact, do the computation by rows instead of by columns. So instead of doing column after column in order to compute the elements of this product, what you do, in fact, is you do it in parallel across all the columns at one time. And it's a rather interesting thing, because what you do then is you pick a row, you go ahead and take this, the vector, you can figure out by using the indices which are the components of y that you'll need for the appropriate values of the matrix. And then in one shot of the vector unit, you take the entire row, which will be very long, and you compute one part of the sum that corresponds to that row. And then you repeat that computation for each row. And as you go through, you're building up all the sums in parallel. You see the idea? So by doing that, partially computing it row at a time, you build it up. And in fact, that's the approach that's used for vector units when it comes to computing these YAs. And for the simplex algorithm, this was excellent. It's a very good way of doing it. It takes very good use of the efficiency of the unit. Good? Now, the trouble is, what happens when we want to compute AX? Well, here's where life got more difficult. And you see, at first you would say, this doesn't sound like such a problem, because if this is one of my sub-matrices I've constructed, and these are all the non-zero values, and I have to compute by something such as by a right vector, that this seems to be perfectly aligned for doing the vector unit computation. There is a difficulty, though, which arises. And the difficulty that arises is these indices of the non-zeros now tell where the answer has to go. So if you just do the computation, you have to know where things have to be added in to this right-hand vector in order to create the product. Say that again. This is you're going to multiply this times x. You do it as you look at the elements, you may have these indices tell you where in the result column you have to put things. So as long as there are no duplicates across any row in the indices, you're fine. Everything works just fine. But If there are duplicate indices here, which can occur, then you have a problem, because your poor vector unit is at the same time trying to add things into the same element. And that's when everything collides. And that was where combinatorial optimization came in. So here was just an example to show you the kind of thing that might happen. This is just showing you the indices. That, for example, if these are the indices showing where the non-zeros occur, and I'm supposing I start with a matrix which had 16 rows, and we had a block, for example, with 12 columns and 3 rows. In this case, we've got problems. So if I try to do the computation, for example, it would say the product from here and the product from here simultaneously have to hit the first row of the result. Similarly, we've got conflicts here. Wherever you would see a duplicate number occurring in a row, that's where a problem occurred. However, there's no reason why you couldn't permute the entries in each row. It does not change anything if you do that, because this is just telling where the non-zeros occur. It doesn't matter where order you put them. So the question came to say, might it be possible to permute the entries in each one of these columns so you could get rid of all the duplications that occur in every row? And this is where the combinatorics began to come in. I represented it graphically in the following way. These are the columns of the submatrix, and these are the rows of the submatrix. So for example, here I've got the 12 columns of the submatrix. Here were the 16 rows of the original, and what the edges simply show you is which cells are non-zero in the matrix. So in this case, for example, the first column has 1, 2, and 6. And that's a bipartite graph representation of this particular matrix. So when I say that I want to permute each of these columns so that I get rid of any duplicates in any row, what am I doing to this graph? Can you see the graph problem that comes out? I'm coloring the edges with one color for each row. And the condition I'd like to have is it's a proper coloring, so that each edge, for each vertex, the adjacent edges should have a different color. And if I can do that, then by putting color 1 here, color 2, color 3 here, I would now have found a permutation ordering of each of these columns in such a way that I removed all the duplications. So that was the application of the Koenig theorem to this particular problem. Now, I shouldn't say the Koenig theorem, it is a Koenig theorem. And this is the edge coloring theorem, in fact, which came into this. It said if you have some number of rows, you can permute the entries in each column so that no row contains duplicates. That's equivalent to an edge coloring. Koenig's theorem says you can do it if and only if you, every node you want to, if you have D colors, the bipartite graph has degree equals D, which is equivalent to saying each index appears at most D times in the submatrix. So what was needed then was an efficient way to, in fact, get the coloring of this bipartite graph. And I don't know about you, but when I first learned the Koenig edge coloring theorem, what was the first proof you learned of it? Do you remember? I mean, the first proof I learned was saying if it's a regular graph, you can find a matching, and you take that matching away, you reduce to the maximum degree by 1, repeat until done. And in fact, when we were talking about this with Jack, or with Alan and with John, the first question was, Bill, don't you have a fast matching algorithm we could use just so we could actually do this? But in fact, that's probably the wrong way to do this problem. There's a better way, which again is an alternating path problem, or an alternating path approach, but which is extremely simple for doing this edge coloring of a bipartite graph. And this was a paper by Faber, Ehrenfeld, and Kirstead. And they just gave this simple proof of this problem. And what it said really is this. You start just by coloring the, so I'm talking now about taking a bipartite graph, maximum degree D, and I want to find an edge coloring of the, coloring the edges with D colors, so that each vertex has distinct colors. And it says, well, here's all you have to do. Start with any coloring you like of the edges of the graph. If every vertex only sees edges of different colors, you're done. If not, some vertex has two adjacent edges of the same color. But if that happens, there's got to be some color you missed in that vertex. So what you do then is you just take an alternating path, alternating between the duplicated color and the missed color, and run it until it peters out. And it will peter out because of the bipartiteness of the graph. It can't fold around on itself. And once you found that path, you simply reverse the edges in it, and by doing that, you've reduced by one the number of miscolorings, and you can go on to that. And that's all you have to do now. It's a nice algorithm. The thing that we found about it that was quite interesting with it is, boy, this was easy to handle in the matrix context. This particular algorithm in the matrix context turned out to be very simple approach. And here, I want to show it to you because it was important for us, we're going to see in a moment, that it was so straightforward. See, what we said is here's the matrix. What I'd like to be sure, what I'm doing is permuting these columns to make sure that the entries in each row are distinct. So I said what we'll do is we'll just start scanning the columns from the left, and I'll ensure that the part that I've scanned in each row has distinct entries. So I just keep running across, and at some point, I'll come to an element here, which is already duplicated in that particular row, such as you see there. And so there's a row that has a duplicate entry. Now, when that happens, because of this condition which says, your maximum degree condition, it says there's got to be some other row which doesn't contain the C1 in this part, because if every row contained a C1, plus this one, you'd have too many C1s. So there's some row which misses it, like there you see with the C2. And then what you're going to do is simply swap those two entries in those two rows. And then once you've done that, you may be lucky and everything works and then you can finish. If not, what's happened now is you've created a new conflict with this C2 you put up here. But it's, again, just between these two particular rows, and then you can repeat it. So you can, you can work on the details yourself, because what this is exactly the interpretation of the coloring algorithm in terms of the matrices. But when you interpret it that way, what happens is that you've got the matrix, you can pull out those two rows, you do the flipping on it, and you're all done. So it's a very fast operation that can be performed. So we took it and we said, let's see what happens now when we actually try the algorithm. And this was a set of standard test problems in the first ones which you see here. These are a few other problems that we put in as well. The couple of points on it. First of all, these are big problems. The smaller ones are 185 rows, 340 columns. Larger ones, basically 100,000 rows, 200,000 columns. This is the number of non-zeros which actually appeared in these matrices. And instead of trying to give you just the percentage sparsity of it, what I put down here was the average number of non-zeros you'd see per column. So you see what we're saying, that it really is the case with these problems. You get very sparse kind of structure which goes in it. The other thing I would mention is that what you're seeing with these results here is what happened after some pre-processing to be done on the matrices, so I cleaned them up a bit. But that's the sort of order that you get. And then here's what happened with the numerical results when we ran it. This is showing the computation of the AX, which is the part we were focusing on. This is showing the YA calculations, the left multiplications, and these are using the interior method to solve those linear programs. One thing you'll notice is, first of all, if you look at the number of calculations of a right multiplication by a vector, you get numbers like this. If you look at the left, you get these sort of numbers. So they're of the same order of magnitude. It tends to be that you use about twice as many AXs as you do YAs in the simplex algorithms, or in the ellipsoid algorithm. Of course, if this were a simplex algorithm, these numbers would be infinitely larger than these numbers. The second thing you notice is, this is the timings that we were getting if we just did the AX calculation without doing the reordering of the columns. If you do the reordering of the columns, you'll see the time drops. In some cases, it's about half as much. In other cases, it may not be quite as much, but it's a significant improvement. And to be fair, we also put in here the time that it took to actually do the reordering. So it had a significant improvement in time on this actual running of the algorithm. And that's what led us to this question. And I must admit, there was a funny conversation that Alan and John and I had. And Alan said, "Bill, do you have any patents?" I said, "No, I never patented anything." And John said, "No, I don't have any either." And Alan said, "Well, I don't. Why don't we patent this?" And we said, "You got to be kidding." And we thought, "No, let's see if you can patent it." So, in fact, this algorithm is the one that was patented, which is called, I think we call it an efficient method of reordering the rows and columns for efficient calculation of left and right matrix vector products. And if you look at the patent, there's actually a diagram that shows how you do it, and it's all explained in there with appropriate acknowledgement to CUNY.
What is the licensing fee?
We offer a special deal on that one. We'll provide it to you for no charge if you want to use it. Actually, it's a funny thing, isn't it? Because we look at patents in some ways and say, these feel like they're being restrictive in people using them. In fact, the intention of it was the opposite, that it was supposed to be a way that it could be put publicly available. But I can tell you quite honestly, to my knowledge, nobody has licensed this from IBM yet. But someday when somebody wants it, we've got the patent in our portfolio. We also, I just put a reference up there to this. There is a paper which a note we wrote, which actually goes through some of the details on this. So if any of you are interested, that's